Welcome to the final lecture of the week, and also the final lecture of the conformal field theory part of the module. We're going to discuss the bootstrap. So let's get started. So if you recall, we had this constraint, this crossing symmetry constraint, this bootstrap constraint on 4-point functions. So let's write it down for 4 identical scalars. So the prime on the sum means that we've extracted the identity operator. So we're summing over all of the conformal primaries that are exchanged when we bring the external operators close together pairwise in this conformal block decomposition. So each of these G factors, they're functions of the cross ratios U and V, and they're fixed, completely fixed by conformal symmetry. So the only thing that's not really fixed here is what we choose for the conformal primaries, the delta and the deltas and also the representations I of the Lorentz algebra, and also the 3-point functions, the C delta I squareds. Everything else in this formula is fixed by conformal symmetry, and so we need to tune the spectrum and the 3-point functions so that this formula will work. So let's say that we have a proposal. We have a candidate spectrum. So you've come to me with some list of scalar primary operators, possibly infinite. You've come to me with some lists of vector primaries, of spin 2 primaries, tensor primaries, and so forth. This list could be very large. It's probably infinite. You're probably going to need an infinite number of primary operators to satisfy this constraint. And we'd like to check whether we can or not. And of course, we're also going to impose the constraints of unitarity or reflection positivity that we discussed last time. And so we're going to need bounds on delta from unitarity, and we also have the constraint that these 3-point functions are real, and so their squares are greater than or equal to 0. All right, so that's our starting point. Now we're going to define f delta I of uv to be a term in this sum. So it's going to be this particular combination, v eta g delta I of u and v minus the crossing symmetry piece with the u and v's exchanged divided by this little bit from the identity operator that we had last time. So that we're going to define these objects, maybe you could call them partial waves. And now we're going to design some linear operators, or one in particular, a linear operator, we'll call it a curly O, such that O acting on the non-trivial primaries, f delta I of u and v, these are all going to be greater than or equal to 0, but O on the identity is less than 0. What is this O? I'm not going to tell you. You could imagine various things. It's really up to you at the end of the day. One thing you could do is you could just evaluate these conformal blocks or their derivatives or some particular combination of the evaluation of these conformal blocks and their derivatives at a certain point, some particular choice of u and v. And you see if those values, you can choose that particular evaluation such that it works this way, so that O of the f delta i's is positive and O of 1 is negative. Now, if that's true, now let's look at what happens when we take this and we put it back into this constraint. There's going to be a problem, right? Because the terms here, these terms here, will all evaluate to positive numbers, whereas the thing on the left-hand side will evaluate to something that's less than 0. And we already said that all of these C delta I's are positive by unitarity, and so that's a contradiction. So if you can design such a linear operator, then you have ruled out your choice of spectrum. We've ruled out your candidate spectrum. So that at a very high level and with not a whole lot of specificity is how the bootstrap works. You design these curly O's, these linear operators, to have this property. You do it cleverly. You probably have to do it on a computer if you want to do it to any kind of great accuracy. And from this, you can start ruling out choices of spectra. So let's be a little bit more specific about the kind of result that comes out of this program. Let's consider a conformal field theory with a scalar primary, I'll call it little sigma of x, of dimension delta sigma, and we're going to consider this bootstrap approach or this crossing symmetry approach for a 4-point function of 4 of these sigmas. So x1, x2, x3, x4. Great. And let's think a little bit about the OPE, operator product expansion of 2 of these sigmas. So if I take 2 of these sigmas and I bring them close together, well, I can get a 2-point function for those operators because it's the same operator. The 2-point function won't vanish. So I've got x to the 2 delta sigma, and then that 1. This is our identity operator. It allows for the possibility of having a non-zero 2-point function. And then plus higher order terms. And the first term we'll call it c sigma sigma epsilon. So there's going to be some 3-point function with 2 sigma operators in this epsilon. There'll be an absolute value of x by dimensional analysis to the dimension of this operator epsilon at 0, and then plus higher order terms. So in other words, this epsilon of x is the leading non-trivial, shall we say, since it's not the identity, in the sigma cross sigma OPE, the sigma sigma operator product expansion. Great. So what might you expect? Let's consider the simplest possible case to start out with. So say it was a free CFT. Say we just had a free scalar field. So with a free conformal field theory, we saw that delta sigma should be what? It should be the space-time dimension minus 2 over 2. And then what epsilon will be, epsilon of x will just be sigma of x squared. Will just be the free operator that we used to call it phi of x before. It will be just that sigma of x squared. And hence we can see, because of that, the dimension of epsilon will just be d minus 2. So that will be the free case. But with interactions, the story can change. It will change. And you can ask, is there some relation, some inequality, some exclusion region in this delta sigma, delta epsilon plane in the dimensions of these two operators where we cannot possibly have a CFT? And that's how the Bootstrap works, or that's how actually it was first applied at least in recent memory. There's sort of a longer history here. The Bootstrap goes back many, many years. It was first proposed with the birth of the conformal field theory program and was later brought back more recently by Slava Richkov and his collaborators. Alessandro Vichy is another name here. David Simmons-Duffin, David Poland, long list of people who've been involved in the more recent incarnation of the Bootstrap, where because of the more powerful computers we have now, we can get more mileage from it. So what you get from crossing symmetry from the Bootstrap here on this sigma, 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 sigma 4-point function, you get a plot that looks a little bit like this. So on the x-axis, I'll put the dimension of the sigma operator. On the y-axis, I'll put the dimension of this epsilon operator. And let's just set the origin. So this is the free case. So the y-axis starts at d minus 2 and the x-axis starts at d minus 2 over 2. So that point there should clearly be allowed. That's the free theory. And what you find is an exclusion plot that looks a bit like this. And then it changes slope, goes off over there. And everything north of that line is excluded. You cannot have a CFT if this dimension of this epsilon operator is too large. You can have it if it's below this line. And you can have it also if it's on this origin point, because that's the free limit. And there's kind of an interesting fact here that little kink in the line, the kink is close, very close to the Icing model in both 2 and 3 dimensions. So there is this idea that these exclusion plots might be able to tell you more than just an excluded region. They might be able to help you zoom in on the actual operator dimensions of special theories. And that turns out to be true, that by considering further 4-point functions, for example, you could look at sigma, sigma, epsilon, epsilon here. You can pinpoint some interacting CFTs. This excluded region, you can make it smaller and smaller. You can zoom on a particular area by considering higher point functions. Not higher point functions, other possible 4-point functions. And it turns out this program has led to the most accurate data for the 3D Icing model. By considering these other 4-point functions, you can zoom in on this little kink area and see that the dimensions of these operators are actually specific numbers. 0.518151, I think, is one of the most recent calculations here, and then for the other one it's something like 1.41264 with some errors that are very small. So what is the Icing model? I said a little bit about it at the beginning of this module. Let's recall what it is. You can write down a Hamiltonian for it. There's some interaction, strength J. There's a sum over nearest neighbors. There's a little variable SI, Sj evaluated on each of these lattice points. SI is equal to plus or minus 1. So, and this is a sum over nearest neighbors. And if we're in 3D, it's on a 3D cubic lattice. That's the 3D icing model. And what is the CFT? What is the CFT associated with it? Well, it's the CFT that describes the phase transition between an ordered low temperature phase and a disordered high temperature phase. So the CFT describes the behavior of the theory at that critical temperature where the theory is on the boundary between being ordered and disordered. You might ask, is there any experimental use for this? And there is. Well, maybe not of this particular model, but we can dress it up a little bit and then we can actually compare with some experiments. So let's do that and we'll bring this lecture to a close. So there exists a generalization of icing. It's called the ON model. And what we do is we promote the SI to a unit length vector with n components. And we perform the same sum over nearest neighbors. And again, there's a phase transition. And I want to focus on a particular case, the case where n equals 2, the O2 model. And now there's a claim that I'm not going to explain or justify that the phase transition for n equals 2 is in the same universality class, which means we expect it to have the same critical exponents, the same dimensions of operators, if you will, as the phase transition for superfluid helium. And now we can go and we can run the same Bootstrap procedure in this slightly more complicated situation where there's basically a slightly different symmetry to the model. Instead of having the Z2 symmetry associated with the plus or minus spins at the lattice points, we now have like a rotational O2 symmetry associated with the fact that these ends are now two vectors. So what we get is we get a prediction from the Bootstrap. This is intense numerical effort. It's not something that comes out of paper and pencil. It comes from putting these crossing constraints on a supercomputer. So the Bootstrap predicts the analog of what we call delta epsilon above, the dimension of the lowest charge zero operator in the operator product expansion of the order parameter for the theory, the lowest operator, the analog of sigma, that it should be 1.51136 with some relatively small error. And then there's an experimental result. It actually has to be done in space to avoid the effects of gravity on the phase transition. And the experiment with superfluid helium says that the same exponent or the same scaling dimension should be 1.50946 with actually a similar error. But you notice there's a big discrepancy here. It's something like 8 standard deviations. There's an 8 sigma discrepancy, which to my knowledge is still unexplained. So you get close to the right answer, but you don't get quite the right answer. And this is still an open problem in the field. So I'll leave you there on this somewhat unsatisfactory note. But physics, it's a work in progress, and I leave it up to you, my audience, to make further progress and try and resolve some of the things that people like me and my colleagues have yet to explain satisfactorily. All right, so that's it for conformal field theory. Join me next week, and we'll start our discussion of supersymmetry.